Right. Welcome to our fourth day, of our workshop on statistical mechanics, integrability, and dispersive hydrodynamics. I would like to remind you that the talk is being recorded and live streamed on YouTube. And I also would like to please ask the online participant to mute their microphone during the talk. We'll be monitoring the chat for questions and ask them at the end. Okay, so with that said, let's warmly welcome our first speaker, Herbert Spohn from Technische Universität München, who will be talking about the two hydrodynamic scales of the Toda lattice.
So thank you. Can you hear? Yeah, okay. So thank you very much for this kind introduction, and also for very pleased to be able to talk, and for this invitation. I mean, Newton Institute was always a dream place to go, and I'm very happy to be back this time. So what I would like to explain to you is this the two hydrodynamic scales of the Toda lattice. So these two scales are, I mean, what I call soliton-based, and the other scale is particle-based. And so somehow the main point of the talk is that I will focus just on one single model. I mean, it will be always the Toda lattice. Now, our chairman and Shenadi and Benjamin, who's somewhere, they wrote a beautiful paper where they actually compare soliton gases and the work in generalized hydrodynamics. And it's beautiful and inspired me, and many of the things which I'm saying, supplement. I mean, this paper. The main difference is that they sort of compare like KdV and the delta Bose gas. And so the microscopic model is, as different as you could imagine. Now here, my main point is that I just want to sort of focus on one single model, and I think this helps better to understand, how the two things are related. Okay. And this will be not a very technical talk. I mean, sometimes maybe I want to show you some of the arguments, but I mean, the main focus is that you understand sort of the broad picture. Okay, very good. Having this said, I mean, let me start with the Toda lattice, which of course was introduced already, but let me just sort of repeat this. So here's my Toda lattice. So you have particles on the line, and there is the kinetic energy. I mean, these are classical particles on the line, and you have this exponential interaction between particles with nearest neighbor. There's no ordering between particles. I mean, that's why I put the picture. I mean, of course, the labels are ordered, but no ordering. I mean, no positional ordering of the particles. Now, you have to put sort of boundary conditions. I mean, we will look at open, also ring and closed. I mean, this you will see as I go along. Now, this is sort of the picture which I call the fluid picture. I mean, I really literally think of these as objects as sitting on the line and, doing whatever the differential equations are telling them to do. Okay. Now the other one is that you can go to the Flaschka variables, and they are sort of somehow more naturally viewed as a lattice field theory, right? I mean, now I sort of start plotting my lattice and I introduce these new variables, and now you see you get such kind of equation where you see sort of some coupling to the right and some coupling to the left. I mean, somehow you have lost a little bit the particle picture, but it's sort of like, going to more like a discretized wave equation. And so of course, it's the same thing. It's the same equation, but, in terms of description, I mean, I sort of switched between both of them. All right. And now the beauty of the subject is that there is a Lax matrix was discovered many years ago. Maybe one thing I didn't mention. I mean, a huge number of people have sort of worked on the topic, and I'm not giving essentially any reference. I mean, that's just sort of because otherwise I would not be able to finish in time. But I'm not ignoring. I'm just sort of cannot display it. All right, and then of course you also have the inverse scattering transform, which I don't have to display because it will just come in words. I will never really use it. All right, now the next picture which I want to show you is basically sort of, to try sort of like a mental massage, so that in order you are convinced, why the picture, should be true. All right. And so here what is plotted is sort of more or less arbitrary. I think we have got already 16 particles on a torus. So these are, so X is going upwards and time goes to the right. And so you see 16 particles, and then all what one did is, so you pick sort of, in some sense at random, some initial positions and some initial velocities, and now you just solve the equation, okay? And that's the picture which you see. Okay, now if you want to understand the connection with soliton gases, you should go from the particle picture, which is sort of obviously plotted here, to what people call the quasi-particles. The quasi-particles are objects which maintain their velocity sort of in the course of time. Of course, they cannot do that always. So then let me sort of show you a little bit one of these pictures. So what is indicated over here, this red trajectory is supposed to be the quasi-particle, right? So you see it's sort of going down here, the first collision, etc. The next one, you keep going. But you see, it's sort of drawn, it has been drawn by hand, but after each collision, somehow you sort of, approximately have sort of like the initial velocity. And so let me just sort of, look at this piece here. That's sort of a very nice sort of essentially completely two-particle collision. So you have these two particles coming in. The positional trajectory sort of overlap, but then they sort of realize the strong repulsion, and then, they continue. And of course, this velocity is the same as this one, and this velocity is the same as this one. Now, if you want to know the true velocities, then what you have to do is you just, take this particular configuration, position momenta, and you compute the eigenvalues of the Lax matrix. Those give you the true velocities. Now, this we haven't done. We just sort of looked at the picture. And the other thing which I want to emphasize is that, this picture is very blurry in the sense that when I'm close to a collision, then of course, I cannot maintain my velocity. So during the collision, you don't really know, what velocity you cannot maintain, you don't know which of the two quasi-particles actually you're looking at, right? Here I have two quasi-particles, here in the middle is blurry. And then, if you come here and then you get this huge region of lots of interactions, you have no idea, what you mean actually, okay? So that's, of course, if you remember Ken's talk, that's, of course, exactly the same as what happens with ordinary solitons, right? Once they separate, but once they are close, you don't. And if you really want to sort of do more experimentally, know what is sort of the collection of velocities of your quasi-particles. Of course, having the Lax matrix is very beautiful. Sort of, it's like a microscope or a filter. I like to call it sort of the Lax filter, because it's sort of, singles for you out the conserved quantity. Of course, the Lax eigenvalues, they are wherever you are. they are exactly the same. But if you sort of want to do it experimentally, then at the end of your experiment, maybe that's your final configuration, then, you remove the boundary condition, you let your sort of particles expand to infinity, and then, of course, the Toda flow diagonalizes the Lax matrix, and asymptotically you will have freely moving particles, and then, of course, you can see what the velocities are. So this is actually, this, at least of my community, this sort of called time-of-flight method, and they actually use it experimentally. When people sort of probe the delta Bose gas and they want to measure what are the spectral parameters, that's how they do it. Okay. Now, of course, it's not, it's sort of, it's not too explicit, right? We have to let the dynamics, but it's sort of experimentally you can do it. All right, so fine. So now I hope I have convinced you that when you look at the Toda lattice on the particle level, and when you look at the quasi-particles, then they behave like what you would think like KdV solitons, roughly, right? Of course, details are very different, but the rough picture is correct. And so let me just support this by a little bit more formulas. And so what I have put for you now is sort of, the other picture, which is the soliton gas of the Toda lattice, okay? Now, for the KdV, of course, this has been studied a lot. Toda, I'm much less aware of sort of detailed investigations, but I'm just sort of, following, the standard rules and tell you what the input are, okay? And so what you have is that if you want to, so now I'm just doing scattering theory, right? I just want to convince you that the scattering theory for the soliton-based picture and the quasi-particle-based picture or particle-based picture is really identical. Okay, and so here this is sort of the famous work of Toda, where he discovered what is the one-soliton solution. So asymptotically goes to 1, and then this is sort of very similar to KdV. So you have a velocity. I mean, so eta is of the spectral parameter, and you have a velocity which is sinh eta over eta absolute value. So you see there's a gap. I mean, so you have it's bidirectional, and you have right and left going solitons, but then there's a gap in between. So all the solitons are actually supersonic. Right? All right, and then in order to do the scattering, I mean, the most important thing, at least sort of, for the purpose of generalized hydrodynamics, is to first understand the scattering, but you want to also know the first order convection. I mean, so you want to know how much, at long times, how much particles have shifted relative to the free trajectory. And so for this, I mean, you just look up the books. I mean, so you find, of course, a two-soliton solution. You can analyze the long-time asymptotics of the two-soliton solution, and this is what you find. I mean, so there are sort of, that's a condition here on the spectral parameters. If the product is positive, I mean, this is what people call the overtake condition. I mean, then you see that it's that particular function. And if you do the other one, which is the head-on, it's that particular function. And here I remind you of the picture. I mean, so you have the solitons coming in. Here's some complicated interaction region. And then at long times, I mean, they're shifted. I mean, they're shifted to the right or to the left, depending on the situation. And if you just have two particles, this one is shifted opposite to this one. Okay, and you see this is actually, if you look at it more carefully, you see that's always negative. So this is sort of, I mean, in my convention, corresponds to particles colliding and then sort of keeping a minimal distance, sort of like hard rods, and then they still go off. And this other one is actually actually positive, and this corresponds to the pictures which you have seen, where the two particles sort of sort of pass through each other and they sort of overlap, and then they separate. All right. Now let me see. Okay. Okay. So now there's actually a theorem. That's by Technische, presumably that there's more work. I mean, but anyway, I mean, let me just quote this theorem, and then what this is basically saying is, I mean, you start with an arbitrary initial configuration at time t equals 0. So you want to have a I mean, the HA goes to 1 at infinity. I mean, so you want to sort of have here. Sort of this first moment to be finite, and then also for the position. So, your initial data are sort of decaying in that sense. And then what he proves is that, I mean, whatever initial condition you take, if you wait long enough, I mean, let's say in the future and in the past, I mean, you will see an n-soliton solution. And if you look at the scattering shift, so of course, I mean, you have the asymptotic velocities. And if you look at the scattering shift, I mean, then it's sort of, just determined by the two particle scattering shift. That's sort of, the hallmark of integrable systems. You have to put some signs, but that's not so important here. I mean, the main point is that the asymptotic shifts, either in the past or the future, are determined by the two particle scattering shift. And this is true for any initial configuration. Of course, you have no idea, when you just put down the initial condition, I mean, you don't know how many solitons you have. I mean, n sort of depends on your initial condition. You might have one, and then, if you want to discover, you have to make a simulation, right? I mean, it's sort of not such a simple way to do it, but it sort of tells you that this kind of idea that everything is determined by two particle scattering is correct. And there's a similar theorem for the particle-based scattering theory. So this is the famous work of Moser. And what you would say is take, again, now I'm in the fluid picture. I mean, take any initial configuration of particles, but take finite n. You see, that's important because otherwise, the scattering theory I'm telling you now would be in a contradiction with the scattering theory which I had before. Before, n is always infinity, so to speak, in this language, right? So now this is a finite n. I'm looking at the particle positions and momenta. And what Moser proves is that indeed, I mean, you have this asymptotic trajectory. You have here, the shifts to minus infinity, plus infinity. The difference from them is what you call the scattering shift. And of course, in front, you see that you see the eigenvalues of the Lax matrix, and here you sort of the fact that we look at quasi-particles. So that's why I have to, this is why I have to change the index from past to future in this particular way. And you compute the two-particle scattering. I emphasize that computing the two-particle scattering in the particle picture is a very simple exercise. Everybody can do, within half an hour if somehow knows what equation to look at. Computing the two-particle scattering shift for the soliton picture is somewhat more heavy, right? You first have to really understand what is the two-particle soliton. Anyway, all right. So and now we are in a situation that you see we have just discussed scattering, but now we are in a situation is that I can think as my basic objects either the solitons or the particles, and so it's not so surprising that. If I now do sort of hydrodynamics, which of course is from that scattering theory, a very high level up, but that's something which people have worked on and which somehow people understand, is that you should presumably get sort of two different type of hydrodynamics. One for the solitons and one for the particles. But the surprising thing, this was sort of noted already, in the earliest paper, and it's still, to me, it's still very surprising. But it just tells you that integrability is such a strong condition that all the extra details sort of don't matter so much. That while of course the scattering shifts which enter into the equation are different, the structure of the equation which you find for the hydrodynamics are exactly identical. Right? So this will come. All right. Now let me see what I wanted to do next here. Okay. So now I wanted to sort of just jump ahead and what I'm now writing is sort of essentially sort of guesswork, and I don't know whether there are any theorems which support what I'm writing, but I think I sort of want to sort of shift to the hydrodynamic side, and so now you introduce your what I call the soliton counting function. You take it so now I'm in a space-time dependent situation. But the spectral parameters are sort of changing slowly in space and time. So that's somehow what I want to do. And now I have this counting function. So this looks at the small volume element and counts simply the number of solitons which I have in there. And as I said, it's at that stage sort of a somewhat vaguely defined object. Of course, I can look at this small piece, and then I do the time of flight method, and of course then I know what okay. And of course, in a small volume, I have a sort of finite number of objects, and so a finite number of eta j's, but they're sort of like a large number, and sort of can hopefully describe this by this counting function. So I put here the density, the local density, and that sort of, then it becomes a probability distribution. Okay, so now you just write down your conservation laws, and the assertion is that there are sort of an infinite set of hyperbolic conservation laws which governs the motion of this counting function, and of course they are nonlinear. They are coupled to something which is called effective velocity, and that's of course is a nonlinear function at a given space-time point, of what I put here dot, right? It's a nonlinear function of the counting function at that space-time point. And now the question is, what is this nonlinear function? And for this, if you sort of, since people have done so much with it, there's a nice shortcut, and the shortcut is to say that, what I have to do is I sort of have to, in some sense, sort of look at tracer objects. Let's say a tracer soliton, just exactly like what Ken was talking about. When the soliton was sort of moving through this conoidal wave. That's sort of the tracer particle, and then you argue that this tracer particle will go with its own velocity, which is that particular function in this case. So there's nothing else. It's just sort of this one soliton. So just a single soliton solution, if you want so. But then of course, it's sit in a medium, and therefore this bare velocity is modified by the collision with the other particles. And the idea is that that's sort of somehow, the effect of collision. This could be either negative or positive. And what is written here is sort of the rate of collision. Okay, so this is why it's called collision rate ansatz. And here's the picture. That's sort of the soliton, which would move bare velocity, nothing else, sort of just sort of on the infinite lattice. But now, if you put on the infinite lattice other stuff, then it will move with effective velocity. Yeah.
Can I ask a question?
Yes.
In this collision, you're considering only binary collisions.
Yes, that's right. Well, because everything is determined by the two particle scattering shift.
So due to integrability, you don't have to add others.
No. In fact, I mean, if I would have to do others, I mean, then presumably, this kind of hydrodynamic pictures which I'm doing would be completely, would be obsolete. I'm going to lose all the conservation laws, and no. I mean, so it's a good point, but yes, I mean, it's always a two-body. Okay, and now this equation you can sort of solve in quote. I mean, it's just if you want to rewrite it, but it's still useful because I mean, that's one of the funny things. It's of course it's the central equation, but the way how it's obtained, I mean, depends very much on how you do the derivation, right? I mean, sort of depending on the derivation, you come up with quite different formulas. But at the end, I mean, you verify that they agree. And so one way to rewrite this equation is that you introduce first of all another important quantity, which is the number density, which is simply defined here. It's just defined by the counting function. So this is always sort of I mean, think of xt being fixed here, right? And it's just that's just the ratio of two functions. I mean, t is this. T is this operator. T is our collision, the two particle collision operator, and okay. So you take this ratio, and then you introduce also, which is a very important observation. I mean, this stressing information of some arbitrary function. So these are all functions on R because they just depend on the spectral parameter. And so here you have to sort of invert this operator. So you do this particular operation, and you call psi is the original function. You call this the stress function. And then you stare at this equation, then you realize that the effective velocity can be written as a ratio of two functions. I mean, one is the sinh eta squared stressed, and the other one is the eta absolute value stressed. Okay. And then once you have this, I mean, then you realize that you can actually use these variables sort of as new variables, and then the magic is that what was here under the differentiation actually is pulled out. And so this is why this is called the normal form. I mean, normal form has the advantage that, sort of numerically, I mean, this normal form is sort of more convenient than this one up here. And then, of course, usually when you pull out, if you try to pull out this object outside, you will get some complete mess over here. But in these variables, the magic is that it's just... All right, so now we have sort of like what would be, the potential hydrodynamic equation for the soliton-based hydrodynamics of the Toda lattice. Okay, now let's see what we have to do for the particle base. It's just exactly the same story, right? I mean, so I don't really have to repeat every word, but it's on that level, it's just exactly the same story. The only difference, of course, is now our basic objects are just particles. So their energy momentum relation is just the 1/2 v squared, and so of course this I have to take into account. So the first thing, so first question is, what is the analog of this soliton counting function? I mean, a nice thing about the particle picture is that now you have actually a very clear mathematical description. You see, what you should do is, I mean, you take your local plot. I mean, you look at whatever, particular time, you look at the position momenta, and you just compute the eigenvalues of your Lax matrix, and you call what people call the density of states. So the density of states is simply, the normalized, I mean, you put just delta functions, so it's a sum over delta functions, and then normalize to 1. And you put the delta functions at the location of the local eigenvalues. So that's one simplification of the particle that what you mean by your counting function is it's just the density of state of a mathematical of a matrix, right? Okay. But then once you have made this definition, then everything goes before. Here I have the bare velocity. Here I do the collisions. Now, of course, this is now the two particle scattering shift for particles. So that's just the difference. I mean, log of absolute value of the difference. But this is the same formula, right? I mean, what was before the F, I mean, the soliton counting function is now sort of the local density of states. And well, then you're tracing, because here, it's just the bare velocity. I mean, the tracing, I mean, here I get, so to speak, 1, it's W divided by 1. So I get 1. And then you do the tracing formula, and then you get the equations of motion, and you see that part. And once I'm on the level of hydrodynamics, of course, what I mean, the details are different, is that it's, what I call rho p, and these things also have slightly different interpretation, but at the end, it's the same structure, right? Okay, so now we have this sort of somewhat amazing thing, is that if I sort of view the Toda lattice on the somehow as where the basic objects are the solitons, then I should use the first set of equations, and I want to use particles as my basic object. I see the second. I mean, is there any contradiction? Well, I mean, not really. At least I would say not really, because you basically look at very different initial conditions. Now, which initial conditions are of more interest? I mean, that depends on how you want to use it, right? But a priori, I mean, there's no real contradiction. You're just focusing on some very different. I mean, starting initially something with sort of a collection of n solitons is a very different initial condition than what you would put in the particle picture. Okay? I'll come to this a little bit in more detail. So the next thing I want to show you is, so now we understand this. I mean, let's open up a little bit, and let's just have a look at other integrable models. Are they soliton-based or are they particle-based? Or maybe both. Okay? So I just want to go through the list, I mean, so that you see that it really depends on the model. And then so I just have listed a few which sort of course there are more integrable models, and you can sort of wonder what they do, but I mean, let me sort of the list is long enough. Okay, so let me just go through the list. I put as very first example, I put the hard rods. So these are just classical particles which have a finite diameter. It could be positive or negative, and then when they do elastic collisions. Okay, so this is that's obviously soliton particle based. I mean, I have no idea how to construct any solitons out of hard rods. Okay, all right. Now I do another system, which is the box ball, which sort of a discrete space-time discrete sort of dynamics, which does have solitons. I mean, they are counted 1, 2, 3. They're just going in one direction. And so the velocities are discrete. I mean, so it's a much simplified model, but this is a model which can be analyzed mathematically in great detail. And the scheme which I showed you, effective velocity, all these things, I mean, sort of translates 1 to 1. So that's completely soliton-based. I'm not sure whether you can construct particle-based, but anyway, I just advertise these things as simple toy models. If somebody wants to do sort of mathematics, I mean, that's sort of an interesting thing to look at. Okay, now let's look at KdV. I mean, that's certainly soliton-based. I mean, I don't see any particles, at least I haven't seen anything. I mean, okay. Now you come to Toda. I mean, then you have both. I mean, of course, if I want to really do the soliton-based, presumably I will have to do a lot of inverse scattering transforms and the sophisticated things which I just list here the name. But what I want to emphasize is that when you look at the soliton and the particle base, you're sort of using different theories, different methods. I mean, so for the Toda, if you want to actually prove something about the particle based hydrodynamics, I mean, then you use scattering theory or you use random matrix theory, because your Lax matrix under random initial conditions becomes a random matrix, and so it's very fruitful to actually look at this as a random matrix and study its properties, right? I mean, so this is why I put here random matrix theory. Now I look at the Carloccio model. I mean, this is classical particles, but now these are sort of particles which are, everyone is interacting with everything else. It's just like a real classical sort of usual particle system, not a chain. And the potential is just a repulsive 1/sinh². I mean, this was sort of discovered by Carloccio. I mean, at least the classical one is the one he sort of pushed. And surprising enough, I mean, you can say also quite a bit about it, but you don't know how to do random matrix theory. The only method which I know is that you do scattering theory. Okay, and when I say something, I mean, I haven't really specified what you can show, right? I mean, it's much less than what you actually want to, but you can do something. Okay, and but here I put a question mark. I mean, if you look at the Carloccio model and you look at inverse a scattering transform, and then you look also at what you do on the scattering side, it looks very much like Toda. So the question is is there a soliton solution of the Carloccio model? I don't know. You see, this would be something which sort of has to contain many particles, And if you're sort of sitting in a sort of somehow uniform background, or maybe things sort of go to infinity, I just don't know. Okay, so I put the question mark. So now for the NLS, I mean, the same thing as KDV. I mean, presumably it's a soliton-based. But when you go to the upper lattice, which sort of this particular integrable discretization of NLS, then you have both. I mean, of course, here all the basic things are available. I'm not aware that people have done it, but you can certainly do it. But you also can do this side. I mean, you can do random matrix theory, and then you get similar results as what we can do for the Toda. Okay? So, here I put no particles. It's something which sort of bothers me, but some point this will be solved. I mean, you do random matrix here, but if you ask me what are the particles in the Abel-Witz lattice model, then at least at the moment I could not tell you exactly what they are. But it's clear that when you look at the structure, it's all particle based. All right, now, okay, so now I come to the last thing, and that's sort of actually an important message, at least sort of I find this important, is that when you now go to quantum models, which of course, physicists, by sort of, when you look towards physics, I mean, they are really interested in these quantum models. They are all particle based. There's not a single model where I know that anything like a soliton actually exists. And the reason is the following, that, when you look at the, when you look at the quantum model, I mean, this sort of intrinsically has already this, in the basic Hilbert spaces has already a particle structure in them. And when you talk about two particle scattering, you might think, okay, it's like Schrödinger with a potential, and it's similar like two solitons colliding with each other. No, because you see, it's now in a wave equation, the KdV or the other equation, that's a wave equation which is sort of living over R. Now, if you take two particles in quantum mechanics, it's living over R2. And so now you have a wave equation in a two-dimensional space. And then, this scattering is sort of a fairly simple thing to handle. I mean, that's what you teach your student how to do it. And of course, you can, in most of the quantum mechanical models, I mean, it's something which you can sort of work out. And so when you actually look at it, it's clear that when you look at your hydrodynamic equation, it's always, this two particle scattering which enters in your equation. And for that reason, I say with high confidence that in the quantum case, it's always particle based. All right. Maybe there are different opinions and we can discuss. I mean, so I see already Benjamin sort of shaking his head anyway. So, all right, fine. Okay, so now what I want to do, I mean, so I still have a little bit of time. So now I want to sort of highlight sort of, a little bit more precisely what to my taste is the difference between, particle-based and soliton-based, always in the context of the Toda lattice. And okay, so I want to discuss two things actually. So one thing I want to discuss is a little bit this issue of local stationarity and generalized hydrodynamics, and the other one, which is sort of this collision rate ansatz, which is sort of one of the central things in this whole story. Okay. And okay, so I have to say excuse. You see, I mean, of course, I've been reading, literature on KdV and similar things, but I never really worked so much. I mean, so maybe what I'm saying is maybe a little bit biased towards the Toda side, but I mean to the particle-based picture. But I still think it's sort of interesting to sort of see what the difference are. Okay, so let's first look at okay. So here I mentioned maybe I should mention some literature. I mean, so as everyone knows here in this audience, but still, I mean, the soliton-based KdV. I mean, that's sort of this famous work of Gennady, and yeah, of course he wrote down in this context. I mean, he called it differently, but of course he wrote down this collision rate ansatz. And then when you go to the particle-based world, I mean, this is somewhat later. I mean, it's these two papers which sort of make the breakthrough. I mean, the breakthrough was actually, that they sort of were able to somehow figure out what this effective velocity would be, right? I mean, a formula for the effective velocity. So these are the two independent work, and it was extremely influential. I mean, this is sort of, that's somehow the starting point of generalized hydrodynamics. Okay, so now, if I just want to say one word about this thing. I mean, so forget about, Toda. I mean, just think of a real fluid, I mean, water, in your tap, and you do hydrodynamics, okay? And then I open the books, and now what people say, in the first chapter is always that it's based on a very simple idea. Namely, when I look at a sufficiently small volume, then the system will be, in that volume, it will be in thermal equilibrium. So once, that's sort of, so once I give you what is the velocity, I mean, I give you the energy or the temperature, then and the density, I mean, then there is this equilibrium state which people have studied since over 100 years. I mean, what you learn from equilibrium statistical mechanics, and the idea so this is called local equilibrium. Now, and then the idea of the dynamical issue, which of course is used in many fields of physics, is that once you have these equilibrium parameters, which typically are few of them, and they live with some space, I mean, like R to the power of degrees of freedom. So you have sort of like a few continuous parameters. They are going to change slowly in space and time. And when I look at some other space-time region, I mean, I will see, again, the thermal equilibrium was with different parameters. And then you ask yourself how these parameters evolve in time, and then you write down the Euler equations, right? So that's the picture. Now, of course, this picture hasn't changed. I mean, but when we do soliton gases and when we do particle-based hydrodynamics, I mean, it's exactly the same picture, okay? And so you see the input which we have is that what I call local stationary. It doesn't have to be Gibbs state, but you have to identify what is your measures which play the role of local equilibrium, right? And then of course once you have that, I mean, that's not enough. I mean, you have to know something about your thermodynamics, okay? And so I guess what I'm trying to say in this, I mean, this you shouldn't read this too much, but I mean, what I'm just trying to say in this thing is that when I go to, let's say, like KdV or so, of course, there's this beautiful modulation theory, and I mean, if you sort of wonder yourself, what would be a typical random initial condition? I mean, this is sort of more like, prescription for dilute gas. I mean, where you have sort of, you just sort of put solitons one by one. You have some random separation, and of course they have also random spectral parameters, and then you take them, all of them independent. I mean, that's sort of what you would think, but that's of course certainly not the most general case. And so I mean, this is just really more a question. I mean, that's why I just here put pressure that I mean, when I look at these works, I mean, and then I try to identify this, I mean, the local stationarity and the thermodynamics. This is why I could put here the pressure. I don't see it in the literature. I mean, maybe Gennady can sort of tell us more precisely, but when I read the literature, I mean, this is never sort of a big point. Whereas when you look at the particle thing, that's the very first thing you have to do. Of course, it's a cheap thing. You see, I'm not saying that it's difficult. I was just saying that sort of considered to be a sort of a really basic building block. Okay, so now I can do sort of the particle. And so let me just show you a little bit how this works for the particles, and of course it's a Hamiltonian system, so this simplifies a lot. And now I put here the sort of in terms of I guess I'm thinking here in terms of the fluid picture, and so I want to just tell you a little bit what this generalized Gibbs ensemble is. I mean, I haven't written down any formula here, but basically, when you usually write e to the minus beta h, I mean, then you simply add up all the conserved quantities in the exponential. I mean, this is sort of what is your generalized Gibbs measure. But the main point which I want to do is that, first of all, in this case, I mean, you have very explicit formula for these conserved fields, right? Of course, they're all, explicit in terms of, the Lax matrix, right? So it's sort of, it's sort of algebraically explicit. And so here you see, you just take sort of like the angled elements of your Lax matrix to the power n. And this gives you sort of the conserved fields. And of course, if I integrate this in space, I mean, then I get the trace L to the n, and this we know is sort of conserved because the eigenvalues of the Lax matrix do not change. And now what comes, and that's sort of something which is very characteristic of all particle-based models. Now, when you ask about the thermodynamics, it's defined through a variational principle. You see, so if you start computing the free energy of the systems, and whenever in these models, when I said it's okay basically means that we know how to compute the corresponding free energy. And so when you compute the corresponding free energy, it's given in terms of a variational formula. Now here I've written down the variational formula for the Toda fluid, but when you look at other models, I mean, basically in any model, I mean, there will be such a variational formula, and the variational formula is over functions of, I mean, sort of densities over the real line. It's sort of, these are, you know, I mean, W is sort of the parameter in spectral space. So these are, if you want to sort of, it's sort of the continuum analog of this density of states. And then you know, then if you sort of want to do thermodynamics, I mean, then you know, if you want to compute the free energy, I mean, then you have to look at the minimizer of this object. And if you want to sort of you know, want to maybe compute average of conserved fields, I mean, then you can do it by differentiate this function with respect to the potentials. I mean, it's just all the usual operation which you sort of know from you know, from your basic course in statistical mechanics. But the key point is that there is this variation formula, right? I mean, so, and the variation formula, of course, you know, when you write down a Gibbs measure, there are variation formulas in very abstract spaces, which are, you know, maybe nice to have, but you know, in practice they are very, very useless. But here it's a variational formula over functions on the spectral space, which are functions over the real line. Okay. All right. Now, okay, so I just wanted to indicate that one way how you can sort of prove this formula. I mean, what you do is you take a very particular confining potential here, which is sort of made also out of exponentials, and L is, so to speak, the size of your box. And so you know, I'm still working on infinite space, and I'm sort of confining the particles, because otherwise, I mean, I cannot define a partition function. But then the transformation to scattering coordinates is actually canonical transformation. So when I write down, for instance, my partition function, which would be an integral over QP with something, I can sort of transform this to an integral over the shift coordinates and the eigenvalues of the Lax matrix. Now the shift you want to get rid of, because you know your partition function just depends on the eigenvalues. It's the trace to the L to the N. But then there's this magic that for this very particular potential, I mean, you can integrate over all the scattering shifts in a very explicit way, and you get an explicit formula for the joint distribution of all the eigenvalues. Now, once you have that formula, I mean, and then you still have to massage a little bit. I mean, maybe a little bit less anyway. So maybe a lot of massage, but anyway, I mean, you can sort of figure out, and you get this variation formula. Okay, so that's sort of what I wanted to explain here. And then let me see what else I have to say. Okay. Yeah, no, that just works fine. Okay, so now the other sort of slightly more technical slide, which I wanted to explain to you, is that this issue of computing the average currents. You see, I mean, thermodynamics is one piece, but you know, we want to somehow get this be effective. I have this collision rate ansatz, which at the moment, at least the way how I present it to you, is sort of like an ansatz. I mean, you know, sort of course, if you do KTV and do sort of modulation theory, then you know, you somehow derive this formula. But I want to show you one derivation, and the reason why I want to, it's a very cheap derivation, you will see in a second. But the reason why I want to show you is that you know, there's one point which I should have emphasized, but maybe it's somehow clear to the audience. The point is that, you know, hydrodynamics should not depend on any kind of small parameter. You see, it should be for any density and, you know, any sort of counting function. You should have, of course, you have this low variation, but otherwise, you know, it should be completely general. I mean, in particular, there's no assumptions on, you know, particles being far away or so. I mean, okay. So then the question is, you know, can you devise an argument to compute the correct effective velocity, which, you know, intrinsically by this argument, you know, it's sort of an identity, you know, it's not some small parameter or something shifting around, but it's just really an identity. Okay, and that's what I want to show you. Okay, so let's see whether we can do this. So here I've written down the currents. Of course, the currents are very easy to compute because you just differentiate, and then you see that they are already sort of the correct form. I mean, so this would be so they have two pieces. One sort of comes from differentiating this PJ. I mean, that's sort of one piece of your current. And then there's another piece which sort of has these step functions in them, which sort of tells you that the X is sort of basically only allowed to be between Qj and Qj minus 1. And here's okay, my Lex matrix, but now you get an object. So this, of course, still depends on the eigenvalues, but now you get, I mean, you know, the lower, I mean, it's the Jacobi matrix. So it's just a lower diagonal. I mean, the lower off diagonal, which is sitting here. Right? And so you see this, of course, is something which now depends also on the eigenvalues, and therefore it's considered to be something very difficult, because all the techniques which we sort of so far have are based on knowing something about the distribution of the eigenvalues, but now you want to know something about the eigenvectors, and of course you're lost. Okay, so this is something, you know, I want to bypass, but the quantity which we want to compute is actually, you know, this average, you know, in the GGE, which I have not written down, but it's not so very important. For what I'm saying, the main point, of course, I'm using that now I'm working on the infinite line, and I have a measure which is actually spatially translation invariant. Okay, all right. So now comes this little argument. So this is something which you know, Takato Yoshimura and myself, we did this sort of. Actually, I was in Tokyo when we worked on this, and so this is based on a very simple observation, namely the symmetry of the charged carbon correlator. Okay, so what does this mean? Well, so I first have to define. So this is a correlator. So there's no dynamics; it's perfectly static. Okay, so here I do just the average with respect to the somewhat undefined GGE underlying measure, and because these objects, you know, when X goes to infinity, they will not decay to 0. I simply truncate that particular expectation. Okay, and then I do an integral over the whole space, and this is what I call the charge, the current, and that's the charge. I mean, so that's a conserved quantity. So it's carbon conserved quantity correlator. Okay. And now you, I mean, that's something which is well known. I mean, you discover that it's a very general fact. I mean, you know, this matrix happens despite its asymmetric definition. Using the conservation laws, I mean, you realize that this matrix is actually symmetric. Okay. I mean, you know, this is, I mean, it's extremely general. It doesn't depend on the underlying model, right? All right, and now we want to exploit this, and the way how we exploit it is that we say, okay, let's try to compute our current. Let's see the nth current, okay? And this is again the Gibbs average, and I put here 0 because I'm in the infinite space, and of course, you know, I have to look at the current density and look at this particular observable at space point 0 or some other point. I mean, you know, it doesn't depend on which point I'm looking. All right. Now I just differentiate with respect to the chemical potential. That's my mu, which, you know, everybody who knows a little bit about statistical mechanics just tells you what you are getting down is the corresponding conserved field, right? So I just get the density of particles. So that has my label 0. So this n stands for this one, and this is the label 0 because I'm differentiating, and I get here my particle density. All right. Now you say, okay, you know, it's symmetric, so why don't we use the symmetry? And, you know, it's the same as B of 0n. Now, what do we have here? Now we have here the nth conserved field. Now 0 is the current of the density, but the current of the density is the momentum, and the momentum is conserved. Okay, and so you see that this one is Q1. That's, of course, a property which is not always true, but for most of the models, I mean, I put here, I think the only exception which I know, maybe other people know more, is the Fermi-Hubbard model with spin 1/2. I mean, there, you know, this kind of trick doesn't work, but for all the other models, in particular Toda or whatever, I mean, it always works. Okay, so here, now why is this sort of absolutely exciting thing? Because you see the Q1 is a conserved, and so it only depends on the eigenvalue. And so what I've written to you is that when I take, if I differentiate with respect to the chemical potential, I get something which depends only on the eigenvalues. But actually, what it depends on is the fluctuation of the eigenvalues, because here you see the covariance of this thing. But, you know, if I know, for instance, let's say the full distribution of eigenvalues, I'm able to compute this. Okay. So you see, it doesn't mean that because there's this differentiation and all these things going on, of course, it cannot be a function of the eigenvalues. It's more complicated. But anyway, I mean, now you can sort of, work this out. I mean, that's a purely static problem. You do this, and once, I mean, let's say you do this for the Toda, and once you sort of have cleared up the formulas, I mean, what you find is that you find exactly in this formulation, you find that it's the velocity trace divided by the constant function trace, and that's one of the formulas which I showed you for the collision rate ansatz. And so I want to emphasize that as you can see, I mean, it's really an identity here. There's no point, some assumption on high temperature or anything of that sort. And it's very cheap and works in many cases. So yeah. Okay, so now you want to do if you want to sort of want to compute now the higher order currents, then of course you have to be effective, and then you just have to take moments, and so this is what you have to put in your hydrodynamic equation. Okay, so let's see. So that's just one thing I want to tell you. Yeah, okay. So now I have maybe 5 minutes or maybe more. Okay, all right. Okay, so now I'm sort of changing gears a little bit because I want to say a few words about work which we have been doing with, I guess, Guido is in the audience, and well, some of the people you have seen. Tamara was yesterday here, and anyway. So so I just wanted to show you, and that's sort of one thing which I always wanted to do, and now we sort of are close, and I just wanted to share with you. You see that I mean, people ask yourself, I mean, why Toda? Maybe there are more interesting models which you can experimentally realize. I mean, that's fine. For me, one driving force was always that, I wanted to have a model where I can do high accuracy numerical simulations. Of course, you see lots of simulations, and they sort of roughly confirm, but they're never really high precision. And now the chance with Toda is that you can really do very elaborate simulations, and you can sort of check. You can sort of do sort of numerically very solid check on the theory. Okay. And of course, now you can sort of dispute, I mean, which quantities to consider to do this such kind of high precision numerical data experiments. But one which I like is sort of because you have a very well-defined initial state, is that I actually work with the Toda lattice starting in thermal equilibrium. So this is now, I mean, the momentum are just independent Maxwellians, and the A's are given by independent chi-distributed. So it's a very simple, just independent random variable. So it's very easy to realize, so to speak. Okay, and that's of course time invariant. And in this state, it doesn't change in time, it doesn't change in space. And so in this space-time stationary situation, I want to compute what physicists call, sort of the obvious two-point correlation function of the conserved fields. I mean, so here you see 2-point because here you have 0, 0, and here you have space, that's a J, and here you have time. And so, I just take here 2 arbitrary indices, but physically, you're not really interested. The full matrix, I mean, would be too many data anyhow. So what we are looking at actually is sort of just a case of the physically interesting quantities, which is a number of momentum and density. So the index n so goes from 0, 1, 2, and that's it. Okay, and so we numerically compute this. I mean, so we take B and beta here. You see, I mean, here I displayed data for beta 1/2, so it's sort of whatever, sort of intermediate temperature, and then I have sweet data plots which at different pressure. I mean, this is sort of, I mean, it's not really very low pressure, but it's lower pressure. I mean, there's sort of anyway, three values of the pressure. Okay, and now there are 2 things we have to do. I mean, one of them is just simply solving the Toda dynamical equations with this particular initial data, and then doing the sampling, right? I mean, so for this, we take a lattice height of 4,000, and we have sort of 2 times which we compare. And you have to do a lot of averaging in order to get sort of not so noisy data. I mean, so this, it's sort of 5 million samples. So you just average over that, okay? Now you're not finished. You see, now you have the bare data, which sort of comes from the experiment, but now you want to compare actually with the predictions of generalized hydrodynamics. Okay. Now this I'm skipping here, but you have to do a little bit of work. I mean, you have to understand, in which way generalized hydrodynamic makes a prediction, but that's a totally standard scheme. But at the end, I mean, you still have to solve. You have to invert these operators and things like this. I mean, so there's still sort of numerical, I mean, much less costly, but, there's still numerical work to figure out what is sort of the correct prediction coming from generalized hydrodynamics. So this I'm skipping totally. So all what I want to show you is, okay. All what I want to show you is sort of, how the two things compare. And so these are, presumably have now better data. I just put one data set. I mean, lots of additional data, but I just wanted to show you. So let's just maybe have a look at the top one over here. I mean, so this curve here is the density correlation. I mean, here you see the off-diagonal elements. So don't look at it, but let's just look at this one. So this is the density correlation, and then the 1-1. I mean, which is sort of the one which has sort of just a single minimum at the origin. That's the momentum correlation. And then the one which sort of has this three-peak structure, that's the energy correlation. Okay. So clearly, there is some variation, but I mean, it's not just sort of too simple. And now, from your distance, I mean, you cannot see even the difference between those data and the one which comes from GHD. I mean, these are sort of black dotted lines which go through. So, there's no fitting. I mean, it's just a perfect agreement. Right? Now, of course, this is at the longest time 600. You see, when you look at so maybe I didn't say that actually. Okay. Okay. So I didn't. Maybe this was maybe an important thing to say here. So when you do GHD, I mean, so this is a correlation function, but on the level of generalized hydrodynamics, you're looking at the scale where this function actually scales ballistically. So, if I would look for very, very short times, I mean, then of course, it's not yet ballistic. I mean, I see deviations, but the point is that so to speak, the thing which you really see, I mean, the bulk part is really this ballistic piece, and it's this ballistic piece which is sort of predicted by GHD. If I want to do correction, then of course, you would have to do more work. And so, when I show you these pictures, I mean, these are taken at a time 600. If I would show you the same picture at 150, I mean, that's the only two times which we sort of studied seriously, then the pictures sort of look more or less the same. But the points where the particles have difficulties to follow GHD are typically sort of, here at the peaks. So at the peaks, I mean, it will sort of be a little, not exactly ballistic, but sort of a little bit below. Anyway, I mean, so this is plotted already, doing the ballistic scaling. Okay. And so I found this sort of, sort of very encouraging because, there are many formulas, but then at the end, get such a perfect fit. I mean, that sort of seems that, we are doing something which actually really works. Okay, so I think that's it. I mean, so I have one simple conclusion is that of course people are working on this, but I want to emphasize is that sort of many of the results which I sort of try to explain here are all static. I mean, they're just talking about correlations and no dynamics, and so this is why I said now for the soliton, I mean the KdV, I mean of course there are also dynamical results, and but somehow I think it's one interesting direction to go is whether this kind of understanding could be also sort of supplemented with some sort of more serious understanding how actually, dynamically, how the full hydrodynamic equation actually comes out of the microscopic model. So thank you very much for listening.
Questions?
So I guess in general, a soliton for Toda is something I should think of as a kind of a parallel motion of several particles or something like that, right? There's a width to the to the soliton.
Yes.
So is there a way to
infinitely many? Yeah.
Yeah, infinitely many, really. So is there a way you can connect the particle and the soliton picture by, scaling the speeds or something so that the solitons become very thin? Each one is basically a single particle.
Well, okay. I mean, okay, there are discussions on that point. So let me just say my sort of personal point of view. I mean, okay, so I have this. I mean, of course, the common equations of motion, right? But then it sort of looks to me that when you do soliton, you're looking in this direction, and then when you look at particles, I mean, you look at this direction. Now you take limits, and then somehow you lose the ability to. I cannot imagine that looking at the hydrodynamic equation, which is soliton-based, that in some particular limit. Of course, maybe we could do some dilute limit, and anyway, I mean, but it would be, yeah, okay. So yeah, even if you take a very narrow soliton, it's made out of very, very many particles, and I mean, you have, I mean, at the end of the day, I mean, you have two very different two-particle scattering shifts. I mean, how to, I mean, you could ask yourself one simple question. I mean, is there in a particular limit where, the particle-based scattering shift sort of is close to the soliton-based, right? I mean, that would be a sort of a more concrete question, right? I mean, yeah.
Thanks.
Right. Maybe one more question.
Yeah, thanks for a nice talk. So it's a question related to a comment you made about people are interested in the quantum context. I mean, it's better to think of it more as having an underlying particle picture, because you're dealing essentially with a linear many particle Schrodinger equation. But on the other hand, we know that you can also describe it in terms of a mean field picture, which leads to the nonlinear Schrodinger Gross-Pitayevsky equation. So I'm just wondering, are you aware of any work that's kind of tried to reconcile the two? Because the solitons in the NLS or Gross-Pitayevsky must be in the linear many particle Schrodinger equation, but it must emerge as a different type of excitation.
Sorry, I just have simply difficulties of understanding what I mean, just acoustically what you're saying. So I cannot really reply. I mean, maybe you catch me right after going for coffee. I mean,
Okay,
then I think we could sort of discuss. Sorry, I mean, it's sort of a certainly interesting question. I mean,
All right. Let's thank Herbert again.